So, yeah, thanks very much for inviting me. Um, it's a packed room. I think it's the packest room in my life. So I'm very glad for you that came here, and thanks very much for that. Um, so I want to present this work, whose title is quite long. Actually, it's a little bit of a mess because we started working or trying to solve one question, and in the middle of the research, we found that what we had done actually could be focused from another point of view, hence the two parts of the title. Um, so we started thinking about what happens if you have a network with more than one layer, and when we project this network, can we go back and unfold this projection? That was the original question. And what we found that by trying to solve this question, the kind of approach that we did was actually doing something else besides providing at least a partial result to that question. That's the reason for the second part of the title there. So right, so this is a talk about networks and time series and their interface. So I assume that all of you have some knowledge about networks. Is that right, Paolo, or not necessarily? Yeah.
Yeah.
So very quickly, just set the setting. I'm gonna be talking about multiplex networks, and these are networks with different layers. So here I put you a couple of examples. On the left, you have an example of a multiplex network with two layers that describe spatial locations. So here the nodes are geographical spots, for instance. And the particularity of multiplex network is that each node is replicated in each layer. Okay, so here node number 2 here has a replica in the second layer, which is node number 2. Okay, it's the same node, so it corresponds to the same physical location if we are talking about spatial location. And then simply the wiring pattern is different in each of the layers, right? It's like having a network where you can make partitions of links with different colors. Another example of a multiplex network can be social networks, where here I'm giving you a cartoon where the nodes are people now, and which are replicated in every layer, and the type of social interaction is different in each layer. So on the top we have Facebook, then Twitter on the middle, and then emails on the bottom. Right? So multiplex and as specific kind of multi-layer networks have been around for a few years now, and so in this work we started by thinking about the following question. It happens that not always layers in a multiplex network are observable. Not always we can say which color has each link. Not always we can separate the colors. Sometimes we only see a projection, and this is the case, for instance, if you consider a person moving around a city, you can use different transportation systems. So for instance, the first layer in this two-layer multiplex network could be the underground transport network, and the second layer here could be the bus transportation network. So it is connecting different spots via different type of links, right? Now, this is clearly a two-layer multiplex network. Now the question is, if now the only information I have about the system is the GPS trace of a person moving around the city, okay, hopping from position to position, then I lost information about the underground and about the bus. I only can see a movement of this walker in a projection, okay, in this projected network. So basically, I have thrown away the colors. So the big question, from a theoretical point of view, is if I have this, is it possible to go back and somehow unfold the true hidden multiplex character. Okay, so that was our main question, and of course, if you think about it for a few seconds, you will realize that in general this is impossible to do without additional information. So by projecting a two-layer multiplex or an n-layer multiplex in just one monoplex network, you are throwing away information, all right? So you cannot go back. So you need an extra amount of information to be able to sort of do the inverse problem, right? To unfold it. So that's what I'm going to discuss now. How by assuming an extra amount of information, we can actually go back. So the first question I want to address is a binary one. Suppose that I observe a certain network. Can I tell whether this is really a one-layer network, or is it just the projection of something richer? Okay, so yes or no. Can I actually detect multiplexity or no? So to respond to this question, I consider the following situation. I'm going to use time series for tracking and sensing my network, and I'm going to use the statistics of this time series to say something about the network. So the idea is roughly is the following. Suppose that I have a multiplex network like this one, and I throw an unbiased random walker moving around this multiplex. Okay, so at some point the walker will diffuse in this layer here, and then it will jump with a certain probability to the second layer and diffuse and jump back and diffuse and jump back and diffuse and so on. Okay, so basically I can define a Markov chain in each of the layers and a Markov chain as the jumps, and my process is fully determined. Now, if this time series, if I record at each time step the position of the walker, that is to say the node where my walker is in each time step, okay, which is this time series here, x of t, and also I record the layer where my walker is at each time step. So that's this time series here. This ensemble of time series fully describes my process, and the process is fully Markovian, okay, just by definition, right? Now the point is, suppose now that I project this this multiplex layer into just one layer, I throw away the colors, okay? That would be like removing the information about in which layer I am at each moment, right? If I do that, the process which originally was Markovian, in general, it's now not Markovian anymore. It loses Markovianity.
Why you lose the memory?
Because basically to be able to track down, okay, can I give you an easier example?
Yeah, I guess.
So it comes from ratchet theory. Suppose that you have your network is just 1D, okay? So when the potential is on, you move with a certain, I don't know, bias. When the potential is off, another bias. So if you switch on and off, on and off, on and off, you will perform a movement here and then off, a movement here, on a movement here, and so on. If now I don't tell in which of when the potential is on or off, I cannot know. So I need the information of my whole history back to be able to say whether I will go right or left.
So the information about the last position is not sufficient to decide your next, and so
yes.
It's not Markov. Yeah?
Exactly.
Because it's path dependent.
Yes.
Well, I still don't see it, but okay.
So this, in ratchet theory, this is what happens, and this is okay. There's a caveat. If the probability of jumping up and down is 1/2, this is not true.
Yes. Okay.
Right. So in that case, it's Markovian. but the probability of staying in one layer is not symmetric.
You don't have the position, and therefore you don't know.
You don't know the connection.
Yeah. So therefore, the whole idea behind how to disentangle truly monoplex networks from multiplex networks that have been projected is to look for non-Markovianity in the random walks. The assumption that we make, and this is a working assumption, is a random walker inside each of the layers will be Markovian. If we assume that within each of the layers the walker moves via some kind of diffusive dynamics, then it needs to follow that if the system is really a projection of a multiplex, then when we look at the movement of this walker has to be non-Markovian. And therefore, if we observe a non-Markovian process, we can then deduce that what seems to be a monoplex is actually a projection of more than one layer. Okay, so that's the mechanism we use to respond to this binary question about whether can we detect hidden layers or not. How we can do that? So yeah, that's what I said. In practice, it's very, very simple and very easy to build up a multiplexity detector, which basically is a measure to compute whether a given time series is non-Markovian or not. So suppose that now what we observe from the network is a random walk or a random walker diffusion over this network. We don't have any more the information whether there's one or more layers. So now we start assuming that this is generated by a Markovian process, and therefore from this time series h of t, we estimate the transition matrix T. Okay. The second step of the algorithm is just now we generate a time series, a realization of this Markov chain. So this realization y of t by construction is going to be Markovian. And again, by construction is up to the, let's say, the Markovian state is going to be statistically equal to the time series x of t. Now, if x of t is non-Markovian, then we should expect to find differences in the statistics of x of t and y of t starting at step 3.
Transition metric is not unique, is it? Given a process, you can have more than one transition metric.
Given a time series, you mean? I mean, if the process is stationary,
I think so.
It's not unique.
Unless you have any number of observations. Okay. It's an inverse problem, so it cannot be.
Yeah, well, we are estimating the transition matrix. Yes. So, I mean, this is the algorithm just finishes by just comparing my original time series and my Markovianized time series, and if we find differences up to 3-step statistics and further, then we conclude that the process is non-Markovian. We can measure those differences by different ways. Here we use the Kullback-Leibler divergence between x and y as the tool to compute those differences. So but that's not really important. You can use other kind of
You can take this here, speaker, I guess.
So, bottom line, so we have a function d, which by construction, so sorry, I forgot to say m is the step. So by construction for m equal 1 and m equal 2, my observable x and my surrogate time series will have the same statistics. So d of 1 and d of 2 should be 0 or asymptotically 0 as the time series in Q. All right? But if the process is Markovian, for n equal 3 and larger, we should expect that this quantity deviates substantially from 0. And that's our criterion for multiplexing. So we can do this with numerical analysis, with numerical examples, and the method basically works well. Here I'm showing you, we have an example where there's a true multiplex with 2 layers. They have the same topology, but different transition matrices. I run a random walker, okay? I remove the information about in which layer I am, therefore the process is non-Markovian in general. Well, it depends on the jump here, as Tommaso said. For r equal 1/2, the process is Markovian, but for other r's, it's non-Markovian. And here we are measuring this quantity here, this d, as a function of the block size. And you can see that for a variety of values of this jump probability, you can still find separation from 0, starting from block size n equal 3. Therefore, you can correctly find that the process is non-Markovian. And under our assumption, that would mean that the random walker is diffusing on something larger than a monoplex. We don't know how many layers it has, but we definitely know that it has more than one.
Sorry, when you say definitely, so this is a sufficient condition for the emergence of non-Markovianity. There could be other reasons for non-Markovianity.
Yeah.
Okay.
Yeah.
Okay.
No, I mean, okay. A fundamental observation is that it is our assumption. We assume that within each of the layers, everything is Markovian.
Mm-hmm.
Okay. Therefore, non-Markovianity has to, assuming this, non-Markovianity pops up because of that. Of course, you can't always have a non-Markovian process in one layer, right? What happens in that case, we will see after. So we can, check this for more complicated structures, and the process basically is scalable. I'm not going to go into the details, but it works for larger and larger systems. But that was just question number 1, which is actually the easy one. Now, the question number 2 is maybe more interesting. Is okay, we have a sensible way of looking for multiplexity, but once we have found that the underlying network is indeed a multiplex, can we tell how many layers does this network has? And can we say something about the topology? Okay, about the links of each of the layers, the whole architecture. So to respond to this question, what we did basically was to use a Bayesian inference approach. So I'm not really sure how much you work on these things, but I'm just gonna give you a very easy formula to remember. What we are doing here in this expression, we are trying, okay, so the probability of my model, my multiplex, having n layers, which is what I want to maximize, given that I observe what I observe, and what I observe is my random walker, okay, is proportional to the probability of observing what I observe, assuming that was generated by a model with a multiplex with n layers, times the probability of actually having n layers, right? So this follows from Bayes' formula. This is called the prior distribution. This is called the likelihood of the model. And this is called the posterior distribution. Okay, and what we want to do basically is maximize this quantity here, or find the value of L, find the number of layers that will maximize this quantity here.
The evidence is missing.
Well, basically it is proportional. I mean, I don't really get to find L. So, so that's what I'm writing here. L will be, so my maximum a posteriori criterion will be, L will be the one that maximizes this the likelihood times the prior. So we assume it's a uniform prior, and then the tricky part here is that to compute this likelihood, I'm going to integrate over all possible configurations. So a model, so a multiplex that will have L layers, and for each of the layers, it will have a given transition matrix. And then I will have another matrix which describes how the walker jumps from layer to layer. Okay, so this set of matrices here characterizes the model. So I'm integrating for a given number of layers over all possible configurations, and that's my likelihood. So there are a lot of ways to do that. I'm not going to go into the details, but we use a certain Markov chain Monte Carlo approach to solve this computational problem. And here are the results. I'm giving you an example, a toy model, to show you how this works. So in this example, the ground truth is, so we have a random walker, and the ground truth is that it's diffusing in a multiplex with just 2 ring layers. Okay, very simple. So in the layer above, it's Markovian, so everything moves in one direction with probability of going towards the right. I think it's 0.14. In the second layer, probability of going towards the right is 0.56, and the probability of jumping between layers is 0.89. So we chose those numbers so that they are not commensurate with the grids of, if you want to do the deterministic integration of this. So the posteriori probability, it picks at L equal 2, so we are correctly finding from a measure of from a record of a random walker, we are finding that indeed L equal 2 is the most likely number of layers. And the cool thing about this approach is that it also gives us, in principle, these quantities here. We can also recover the weights of each of the links. So basically, we can reconstruct the whole architecture. And the reason is because we are doing an adaptive importance sampling when we compute this likelihood, and we are already focusing on parts of the space where there is high likelihood. Okay, so not going into the details, but basically, so the system has three parameters, and the ground truth are the red dots. This one, and this one, and these are the Monte Carlo samples. You can see already each of the samples already falls short, close to the ground truth.
There should be some penalization on the number of layers, because otherwise the best solution is the infinite number of layers.
Yes, we'll come to that.
Okay.
Okay, I can tell you now if you want. We are putting penalization. Where is it? Okay, in words, if we penalize those configurations where 2 layers are very similar. And the meaning is, suppose I have 2 layers, one configuration with 2 layers, and another one with 3 layers, but where there are 2 which are the same. So that doesn't interest us. Yeah. And by doing that, you get this non-monotonic behavior in the likelihood. Right. So okay. The toy model works. Actually, computationally, it's well defined and so on. The big problem is that if now we want to use this in real cases, in real applications, it's a mess. It's a mess. I mean, it's hidden Markov models. They scale very badly with system size and so on, right? So if we think about I don't know, a network with 1,000 nodes or things like this. This is totally out of reach with this approach. Okay, so this is a big open problem for network scientists. If you want how to scale this kind of Bayesian inference algorithms to deal with larger number of nodes. Now, instead of giving you a network science application, I'll give you a biological application. I know we are in a financial group, but hopefully this will resonate somehow. So instead of DNA, you can think of stock price or whatever. So this is the real case application is the following. I'm considering the dynamics of an enzyme called RNA polymerase, and this is a small molecule that lives inside the cell, and it performs basically dynamically performs two things. When it attaches to DNA, and when it is in a so-called active state, it basically replicates DNA. So it basically performs some kind of walking in the DNA strip. Because, of course, the cell is a very noisy environment. It's not a ballistic movement. It will perform some kind of wiggling, okay? So people think that this movement is similar to some kind of ballistic diffusion. Now, from time to time, this replication stops because it doesn't work well. And when it stops, it goes into the so-called backtracking movement, which is trying to get rid of this stock, this molecule. That's what it does. And when it's in backtracking, basically, one can assume that the dynamics of the RNA polymerase is similar to just unbiased Brownian motion, okay? Because it's basically fluctuating in the cell and not doing much more. Now the cool thing is that this molecule switches from an active to a passive state all the time, okay? So this is real measurements. So that's time, and that's the position in base pairs. So basically, that's like one-dimensional position of RNA polymerase. And you can see, first of all, that it's very noisy. But clearly, you can see parts where there's a clear drift. Okay, that would be this kind of thing. And there are parts where there is a clear like stalling, and that would be more similar to the backtracking. And there are alternations. Okay. However, biologists think that there are alternations inside the noise as well. Okay, so for instance, I'm zooming here the red part here. It's not clear when that happens, but they do think that the molecule is also here alternating between elongation and backtracking. However, it's because it's so noisy, the cell, we cannot really see that, right? So we are going to use our approach to try to investigate these kind of processes. The analogy is might be a little bit far away, but it's not that far away. We are using the ratchet analogy. So the idea is, suppose that we embed this time series, which is this movement of RNA polymerase, we embed it in a sort of one-dimensional chain graph, okay? Maybe with periodic boundary conditions like this one, okay? Elongation, which was, I remember, it was similar to a ballistic diffusion, is a Markovian process. When the process is elongated, it would be like if my random walker was performing some kind of diffusion in this layer. Now, when the system switches, when the RNA polymerase switches to a backtracking state, it's basically like going to another layer in multiplex, and now here performing another kind of Markovian process. Okay, so switching on and to the elongation, to the backtracking, and back to elongation, and so on and so forth, would be like doing a random walk in this two-layer multiplex. Okay, that's the analogy with our approach. If things work correctly, because I don't know when my system is in the elongating phase or in the backtracking phase, okay, I'm switching between two Markovian processes, but I don't know when I'm switching, therefore my process should be non-Markovian. Okay, that was our hypothesis at the beginning. And then, if everything works well, then my network reconstruction scheme should tell me that the most likely number of layers to be able to reproduce this process should be L equal 2. Okay. Then that's what we do. So that's basically one example of a time series. Which first we do this multiplex detection to check whether the process is or not Markovian, and it's clearly non-Markovian because for m equals 3 and larger you get this deviation from 0 for this quantity between which I recall you makes the distinction between the actual time series and the Markovianized time series. And then once we do the Bayesian inference thing, we get the posterior measure that peaks quite emphatically at L equal 2. So a possibility can be that these two layers coincide with two different dynamical regimes for the RNA polymerase, which would be the elongation and the backtrack. Okay, so how am I doing with time, Carlo?
So looking at that, still 10 minutes.
Yeah. But we started 10 minutes later.
Okay. So, right. Of course, what you have observed here is that, I mean, the application I presented you is not necessarily I'm not unfolding a true multiplex architecture. I'm just assigning layers to each of the different dynamical modes, right? So by observing this experiment, this application, we can find that actually the approach is slightly more general than just trying to unfold hidden multiplexes. What we are doing basically, sorry, I'm just gonna quick. What we are doing basically is taking a time series and decomposing this time series, right, into our multiplex model. Okay. Now, if the time series comes from the movement of a random walker, then those layers can actually be hidden layers that have been projected. If the process, but the process does not need, in principle, to be a random walker over a network. It can be a general time series, which when the time series is non-Markovian, then we can do the same thing about trying to find the adequate number of layers to be able to reproduce this kind of dynamics. So we are giving a sort of decomposition of non-Markovian processes into a Markov switching combination of Markovian processes. Each of the layers would be a different Markovian process. I have a Markov process that switches between layers, okay? So it's not like, you know, in Fourier theory, you decompose a signal into a sum of harmonics. Here you're decomposing a signal into a stochastic combination, if you will, of different Markovian modes, using the jargon of Fourier theory. Because the idea is general, we can apply it to time series away from random walks. And here we did that just to give you a flavor of the results. I'm looking here at two specific stochastic processes. Well, this is maybe more closer to financial time series, so that's good. In blue, it's I consider an Orsten-Uhlenbeck, which is a well-known stochastic process, which is Markovian. So basically, you can generate like this kind of equation where this is white. Okay, so that's a very, very simple algebra equation. and that's the blue. Okay, so I consider an Orsten-Uhlenbeck, and then I consider what I call a color stochastic process, which basically is the same equation, another variable, but now when my noise term is now an Orsten-Uhlenbeck process. Okay, so here in the Orsten-Uhlenbeck, the noise term is white, and in the color process, the noise term is an Orsten-Uhlenbeck. So X is Markovian, and Y is non-Markovian. And here are the results. So I take so I generate time series of those processes, and I apply the whole framework. So for the multiplexity detector, one correctly finds that the Orsten-Uhlenbeck is indeed Markovian. There's no signs of non-Markovianity, and whereas the colored process generates time series which are non-Markovian, as you can see for m = 3 or larger, then there's a jump in this distance here. When we do the inference approach, we find that for the Orsten-Uhlenbeck, the most likely number of layers is L = 1. Okay, so we only need in general one layer to explain the whole process, which makes sense under our approach. Whereas for the colored stochastic process, which is non-Markovian, we need 2 layers, exactly 2 layers to be able to reproduce the time series. Okay, so just to repeat again, this approach provides a way to decompose a non-Markovian process into a stochastic combination of Markovian ones. I think a cool thing here is that you need to understand that the process can be fully non-Markovian, meaning that like infinite order non-Markovian, and you could maybe need only 2 layers to be able to explain this process, right? So the decomposition is carrying a drastic reduction in complexity, if you will. Okay. So just to end up with this, as Tommaso remarked before, you need a likelihood to be able. Sorry, you need a penalization to be able to have a maximum in the likelihood. Or otherwise, just by overfitting, the likelihood will increase as the number of layers increase. So if we impose a prior, which makes sense, which we want to penalize similar layers, then the likelihood reaches a maximum for a finite number of layers. And in this sense, we claim that we are doing some kind of optimal reconstruction in a way that, of course, needs to be explained and further investigated in further work. But then a question that you might be asked, actually, one of the referees asked for this, was, okay, can you always reconstruct any kind of non-Markovian dynamics this way? So the answer is yes. And we can actually prove rigorously that you can always reconstruct it like that. The downside of the proof is that it's not. We cannot offer a constructive way of finding the optimal, the smallest number of layers that can actually reconstruct the whole dynamics. We can only find a very very loose upper bound. Okay. So the theorem is not helpful to find the actual best configuration, but it guarantees you that there always exists one which is accurate enough to explain the whole dynamics. So these are the theorems, but jump. So summary of results. You see, we started with one problem. We wanted to understand whether one can unfold a network once it has been projected, and we ended up finding that this approach can be useful to decompose a time series. That was the reason why the two titles. So the first point is that we develop a very, very extremely simple multiplexity detector, and then a whole Bayesian network inference approach to estimate the most probable number of layers and the most probable topology, the full architecture of the hidden multiplex structure. And then we showed that the results can be generalized to arbitrary random sequences, not just random walks. And we claim that under this generalization, the method provides a stochastic decomposition of the time series or of the normal Markovian process into a Markov switching combination of Markovian modes. And we proved, well, I haven't discussed how, but you can read the paper. We proved rigorously that such projection is always possible. So that's pretty much it. So here is the reference. You were asking Paolo about how to publish there. I can tell you it's a pain in the ass because the paper was like 15 pages, and once it's published now it's like 40 something. So no one will ever read it because of that. So I don't recommend you to try to do that kind of journal. So, and then just let me thank you, a great collaboration team. For the part of signal processing, Joaquin Mírez and Inés Pérez from Madrid. From the part about networks in this work, Enzo Nicosia from Queen Mary, which is where I work, and Jesus Gardeñes from Zaragoza, and people that did the experiments for the RNA polymerase using optical tweezers and very cool things. Ana Lisica she's now, well, actually she's here. Maybe she's here. No, because I don't know her physically, so just by Skype. So sorry, by email. Edgar Roldan in Trieste and Stefan Grill in Dresden. And thanks very much for your attention.
Thank you very much for your talk. Yeah, that's perfect. We have 10 minutes for